Okay, so let's continue with the local linear embedding, part 3. So the literature for this part will again be these two papers. And we will talk about some results here, in particular the results in this paper about the asymptotic behavior of the LLE under the manifold setup. And we will understand what it means by manifold learning when you use locally linear embedding. And really, can we get the manifold back? Or if we can get it back, in what sense? So remember, recall this is the manifold model we consider. First, we do not consider boundary, and we assume the data is located on the manifold. And I will not repeat everything again, but we always assume we have a good manifold, and you have a random vector that samples from the manifold, and the density function has sufficient regularity. Okay. And we will then, with the density function, that model, we will sample from the random vector x n point identically. And if you have a function that is continuous, then we do some discretization in that way. Okay, so that is the sampling scheme. And remember, we have the kernel, and the theorem we discussed in the second lecture tells you that actually the kernel is very interesting. It's not symmetric, okay, but it is very good. It is a Hilbert-Schmidt, and it is a combination of zero-one kernel and the curvature. And if you recall, this kernel has this tx. Okay, this is tx. Okay, that is an augmented vector in a continuous setup, and this augmented vector captures the curvature, and it includes the interaction of curvature and the regularizer. Okay, so that the kernel is actually data-driven and depends on the geometry. So that is what we have discussed. So just very quick recall of what we discussed in the second lecture. So now let's continue with the second topic, the asymptotical expansion, when there is no boundary. And what do we really get of the LLE matrix? So if you recall, before when we discussed diffusion maps, we know that asymptotically, a diffusion map under the manifold setup, if you do some proper normalization, which we called alpha normalization, right? Which is the normalization that reduces the impact of the non-uniform sampling, then you will get the Laplace Beltrami operator. And we also had some spectral convergence theorems telling you that the eigenvectors of the graph Laplacian will give you eigenfunctions and eigenvalues of the Laplace Beltrami operator, so that you can apply the spectral embedding theory in differential geometry to almost isometrically embed the points into a Euclidean space, so that in some very special cases you can achieve dimension reduction and so on. But LLE turns out to be very tricky. It may not give you Laplace Beltrami operator, may not, even if you have very similar conditions with diffusion map. Why so? Because of the regularization, which we will see in a bit. And this is the question we want to ask. If you recall, QF, this operator, is what we get asymptotically of omega x transpose f vector. That is one point, okay, x, and you have the Q operator, which is normalization of the A operator. And if you recall, what is A operator? A operator, if I remember I put it here, right? This is an A operator, which is an integral kernel. And this integral kernel actually is related to the barycentric coordinate. And if you forget about it, please recall what we discussed in the first lecture and the second lecture. Okay, so we want to ask, what will this kernel, what will be this integral operator converges to when epsilon goes to 0? Okay, this is already in continuous setup. What will happen when epsilon goes to 0? And remember, what is epsilon? Epsilon is the bandwidth, which is the size of the epsilon ball you use to determine the neighbors when you evaluate the barycentric coordinate. Okay, so now let's set C to be epsilon raised to power d plus rho, where rho is a real number. Okay, the d is the dimension of manifold, you remember? So let's say this C is the regularizer. And we want to ask, how will rho impact the performance of LLE? By understanding, by analyzing how this QF will converge when epsilon goes to 0. That will be a question we want to discuss in this lecture. Okay, now I directly show you the theorem. The theorem, you can find more complicated version in the Annals of Statistics paper, but what it tells you is, here, suppose function f is C3, the density function is C5, and we need this C5 regularity because we need to do more expansions to observe how the regularizer and the eigenvalues of the covariance matrix interact. Then the QF of x can be written as C1x plus C2x times epsilon squared plus higher order epsilon cube. Okay, that is the result. C1 and C2 will be something we need to discuss in a bit. And here, let's denote R to be the rank of Cx. Okay, the rank of Cx. And here is something you want to pay attention. In the end of the day, this is Cx. And what we know is the top D by D matrix, this is P minus D, P minus D. Everything here will be identity plus some correction. But that is of higher order term. And you have some constant for sure. This is epsilon D plus Q constant. Okay, but what about here? All the eigenvalues starting from D plus 1, D plus 2. When we say the rank of Cx is R, where R is in between D and the P, it only tells you that lambda of some D plus K is not 0. It is possible that D plus K is epsilon raised to 1000. It is also counted as a rank, no matter how small it is, as long as it's non-zero. So you can start to see the challenge. Okay, although you may argue with numerical accuracy, like the resolution of a computer, but let's forget about that for a moment. You can see, that is something that can be an eigenvalue and contribute to the rank. So this is a small detail you need to pay attention to, the meaning of a rank. Okay, then what is the result? The result is, suppose R is D. Really, there is no normal component. Everything only lives in the tangent space. Then you get C1 is 1 over D plus 2 constant, and you get Laplace Beltrami operator, and you get nabla F, nabla P divided by P, and you get some extra strange term, which is nabla F, nabla P divided by P plus some correction. And here is the interesting thing. You see the correction is epsilon raised to power rho minus 2. Okay, but C2 is 0. That is when R is D, the rank is D. Another extreme is when a rank is full. It's full rank is P, then in this case, you will get something a bit, well, actually quite crazy. You see, this guy is here. Okay, you can see C1 is almost the same, but you have some normalization. And this normalization is actually very complicated. You have 1 minus something, and you take the summation from d plus 1 to p. That constitutes of all the normal directions. And here you can see it's lambda I2, this is the correction term, and epsilon rho minus 2, and the N0 is actually the second fundamental form. Actually, to be honest, after getting this format, we cannot really do too much interpretation of what we get. That is what we can. We calculate it, but what is the meaning? This is very, very complicated. And the C2 as well. You can see C2 is something, well, even more complicated. You have HF. HF is something, well, just whatever. This is Hessian, and this is, well, I just don't know what it is. You just get a lot of terms. And you can control the order, control the size, but it's hard to give too much geometric interpretation and with some normalization. And you may say, oh, this is already super complicated. But trust me, when R is in between, it is more complicated. So I don't really give it here. If you have interest, you can go to the paper and see it. The interesting fact is here. You see, this is rho minus 2. Rho minus 2, isn't it? And what is it? It's rho minus 4. This is rho minus 4, rho minus 4. So what it suggests is the following. Suppose you choose rho to be something sufficiently well or proper, then maybe you can remove all these complicated terms. And turns out you can do it. For example, you can imagine, suppose rho is 3, let's assume rho is 3, then this becomes epsilon, isn't it? If this is epsilon, it means this is very, very small. Then these two terms disappear, right? These two terms disappear. And here, the same. Moreover, if rho is 3, then what you see is here is what? This is epsilon minus 1. Epsilon minus 1 is what? Is super big, right? This is becomes super big. And if it is super big, 1 over something super big becomes very small. So this 1 minus is reduced to almost like 1. So this expansion suggests that you want to choose rho correctly, otherwise you may get something wrong. What it tells you is, suppose rho is less than 2, you choose rho incorrectly. Well, not incorrectly, but you just choose rho to be less than 2. Then you see, C1 depends on the density function, and the C2 is 0. If rho is 3, what do you get? Laplace Beltrami operator, right? Because this density function is gone. Density function is gone because of the choice I told you, right? And if rho is greater than 4, then the situation becomes very complicated. For example, if R is D, you still get Laplace Beltrami operator, C2 is 0. But if you have normal direction and a 4 rank, then sorry, C1 becomes this guy. And what is this guy? I just don't know. This becomes very, very complicated. And also C2 pops out and play a role, which is very difficult to do the interpretation. Okay. So you see, this depends on the density. Okay. This is the ideal situation because we get Laplace Beltrami operator so that we can apply spectral embedding theory. And this is just crazy. I have no idea what it is. Okay, so it summarizes as regularization these two various results and is critical. So the main theorem is the following. Suppose you choose rho is 3 and you choose epsilon and n such that epsilon and n satisfies these two conditions when n goes to infinite. Then with high probability for any xi in x, this should be 1 minus n minus 2. This is minus 2. Okay? Then 1 over epsilon squared. And as I told you, this is WIT. Okay, this is the discretization. And this is barycentric coordinate, remember? Subtracted by f and fk. Sorry, this is xi. This is xi. This is xi. Sorry, this is typo. This is xi. Then you get Laplace spectrometry operator with some higher order correction. So you see something interesting immediately. First, there is no normalization independent of non-uniform density. The normalization has been automatically carried out in the barycentric coordinate evaluation, which is very interesting. Second, the convergence rate, at least pointwise convergence rate, is the same as diffusion map without alpha normalization, which is, again, good. And there's a very interesting phenomenon if you play with it. For example, if manifold is symmetric, like a sphere, and you choose rho to be 8, okay, that is, you choose a very, very super small regularizer, then what you get is a fourth order differential operator. You get fourth order differential operator. If P is 2, S1, you get fourth order differential operator. And what does it tell you? Or what can we do with it? It is still unknown. We don't know how to use fourth order differential operator at this moment. Maybe we can use it to detect symmetry. Who knows? But we don't know. We have no idea how to use it. But this is just an FYI, open question. And this is an example which you can see more details in the paper, but it just tells you that, oh, suppose you have non-uniform sampling on S1, then you do rho is 3, rho is minus 5, and rho is 8, then you get actually quite different behavior of eigenvalues and so on. And this is eigenfunctions behavior. So what it tells you is this numerics support the theoretical result, at least on this one-dimensional sphere. And you can play with some more complicated spheres, more complicated manifolds, and they work quite well. You can go to the paper and see what's going on. And this is another example. This example is a two-dimensional random tomography. Actually, this database will be detailed in another lecture, so I will not go through everything. But the basic idea is, if you have a Radon transform, then the Radon transform, R psi is the object of interest. R psi actually will play a role as mapping S1, one-dimensional sphere, canonical one, into another one-dimensional manifold that is diffeomorphic or homeomorphic to S1. That is what you have to assume. Okay, you assume that psi has some specific properties and the embedding is good, discretization is good, so that this R psi is kind of give you a good one-dimensional sphere, one-dimensional manifold. Under this assumption, okay, you can sample, under this assumption, you can sample uniformly on S1, so that you have a non-uniform sample on the right-hand side, and the goal is, can you recover S1 from the samples on the right-hand side? That is the question. And this is the result. So this is the Chevalier-Logan-Fenton. This is two projection. These are two projections or two data points in high-dimensional space. And this is a PCA. Using principal component analysis, the top three, and you can see that you do not recover S1. There is an intersection. And if you run diffusion map without normalization, alpha is 0, then you can see this is not like a circle. It's diffeomorphic to circle, but you can see some kinking. I mean, this reflects the non-uniform density function. If you choose alpha is 1 diffusion map, nice, this is S1, right? And if you choose rho to be minus 5, then as predicted, it will depend on density function. So it behaves like diffusion map with alpha 0, right? And if you choose rho to be 3, then as predicted, you will get Laplace spectrometry operator of S1 back. So it's very nice, this circle. But if you choose rho to be 8, what do you get? this is embedding. And seriously, I don't know what it is. It is very strange. Okay, so it suggests that if you do not do the regularization properly, then you run into trouble. And the selection of the regularizer in the original LLE seems to hit the sweet spot so that it performs quite well. So the take-home message is, first, kernel is asymmetric. Local covariance matrix captures geometry as predicted, and as well as the augmented map vector. So regularization is critical. If you select it correctly, you can get a Laplace Beltrami operator. It will be independent of non-uniform density, and the convergence rate is the same as graph Laplacian and diffusion map with alpha normalization, which is nice. And this convergence rate is pointwise, and you can generalize the spectral convergence to this setup when there's no boundary. Okay, but well, that we do not discuss. That is it for this one.